Good afternoon, everyone. Sylvia, is this audible back there? Right. It is such an honor to be back here in Michigan, in this building where my career first began. I want to start out by thanking the faculty, Professor Bhattacharya, for nominating me and selecting me for this honor, and to Sylvia for so thoughtfully curating and planning every detail of this visit. It's been incredibly meaningful to be welcomed back in this way. Walking into this building this morning brought back so many memories. It feels a little bit like going back to your parents' house. No matter how grown up you think you are, you still feel like a kid when you walk over here again. And it's just like the smell of coffee, and I could remember the hum of the cryo pumps, and my PhD dissertation was right here across the corridor. This place has given me so much, and it's taught me not only the technical skills that have been applicable throughout my career, but also given me the mindset to approach hard problems with perseverance and curiosity. And that's what I'm going to be talking about today. My talk is called Michigan to Moonshots, and I'm hoping to walk you through, so here's an overview of what I'll talk about. We'll start off with a little bit about my career journey that started here in Michigan as a graduate student. And I'll talk about where I'm now, which is Planet Labs. As Dennis introduced me, I'm the Senior Director of Space Programs and Systems Engineering. I'll talk about some of the key failures that I've encountered while working on moonshots and why they matter. And finally, I want to share some important lessons and takeaways for some of our budding engineers and future leaders about what it takes to build complex systems and lead teams through high-stakes environments. So before we begin, what is a moonshot? A moonshot is a term used to describe an ambitious, an audacious, groundbreaking project or an idea that aims to achieve something that was previously thought of impossible or truly extraordinary. And so the name comes from the Apollo space program that put first humans on the moon in 1969, a mission that seemed nearly unachievable up until that point, but became a reality through focused efforts, innovation, and risk-taking. So where did it all begin? It began right here in this building. I came to Michigan from Mumbai, India, as a 20-year-old with 2 suitcases, a big dream, and no idea what 20 degrees Fahrenheit felt like. I still remember trying to navigate the first few days, figuring out the bus system, decoding how American small talk works, and just trying to not look lost while doing all of the things. This was such an exciting place to land here. It was buzzing with ideas and possibilities. And so really, this was my first moonshot, coming here and taking a chance on this big dream in Michigan in Professor Bhattacharya's lab. And so at Michigan, my PhD work was focused on gallium nitride system quantum dots. And our aim was to realize high-temperature single-photon emitters. What made this experience really unique and was how end-to-end it was, even though it was a focused PhD where I got to go really deep into a subject. I wasn't working on just one part of this project. I got to work on everything end to end. I got to build the entire stack. So it started with the fundamentals of band gap engineering. So designing the heterostructures to confine carriers at the nanoscale, using quantum dot layers that produce these discrete energy structures across which we see single photon emission. Then the next phase was the material growth. This meant I had to develop an understanding for material science, crystal structures, and also the mechanics of how MBE systems work. So tuning the temperatures, the fluxes, to make sure we could achieve the perfect quantum dot interfaces with high quality, exactly the composition and dimensions that we needed. And then came the nanofabrication, where we took this MBE-grown material and built photonic devices right here in the LNF into functional LEDs or single photon emitters. And then finally, I got to work on the optical and electrical characterization of these devices as well. So this involves setting up photoluminescence, electroluminescence measurements, second-order correlation measurements, time-resolved measurements, and all of this really helped me understand the fundamental nature of the materials that we were growing and the devices that we were fabricating. And this full stack approach gave me an instinct for how early design choices ripple through the entire system. And this perspective has shaped every role and experience ever since. So what was the problem that we were trying to solve, this first moonshot that I speak of? So single photon emitters are fundamental building blocks for quantum systems like quantum key distribution, quantum cryptography, and some types of photonic quantum computers. So what we wanted to do was make these devices more practical, compact, and robust. And we wanted to be able to operate them at much higher temperatures because these are typically cryogenic devices that operate around 4 Kelvin. And then how did we solve this? We leveraged the indium gallium nitride material system and quantum dots of that material system to be able to demonstrate this at much elevated temperatures. And we could do this because of the wide band gaps of this material system, really large exciton binding energies, and the high radiative efficiencies that we could produce in these quantum dots because these were grown using really high quality MV growth. And then we sandwiched these indium gallium nitride quantum dots in a gallium nitride PN junction and were able to produce single photons through electrical excitation. And previously, this was typically done using an external laser where it was optically pumped. And now you could really make this entire system a lot more compact and practical. So this work resulted in multiple publications, and we got to talk about this in various conferences. But really, I think the key milestone here was the fact that we built this body of work, which was sort of fundamental and new. And ever since, there's been a lot of research that has followed on to demonstrate more and more practical single photon emitters in using gallium nitride quantum dots. So after I finished my PhD at Michigan, I moved to UC Berkeley for a postdoc in Professor Connie Chang Hasnain's group, also in EE. And here I focused on indium phosphide materials, particularly for silicon photonics. And my work here involved the growth of indium phosphide nanostructures, and we call them nanopillars. So here's a SEM image of those. That we could grow directly on silicon with excellent position control, so we could really tune exactly where we would grow them. And beyond the first couple of nanometers, these materials demonstrated extremely high material quality. And we were also able to incorporate some indium gallium arsenide quantum wells in them, which meant that we could get emitters that were operating in the telecommunication wavelength range, so between 1.3 to 1.55 microns. And so using this technology, we were able to demonstrate LEDs, nano LEDs using these nanopillar devices, as well as edge-emitting lasers over pretty large areas of silicon wafers, actually. And this was a pretty important step towards scalable photonic integration on silicon. And then this work resulted in a couple of publications, and more importantly, it gave me the expertise in a brand new material system on a new technology for a different application. And while I was at Berkeley as a postdoc, I used to use the clean room there. I ran into a scientist who was an industry user, and serendipitously, she happened to be a Michigan alumna, and we had crossed paths in the LNF. And she told me about her work at a quantum computing startup. And I was fascinated that quantum computing had actually made it into industry. So the more I learned about it, I got to go see their lab. This was a little known startup back at the time in Berkeley called Rigetti Quantum Computing. But I was seriously impressed by this team of mostly academics who now had the Silicon Valley capital to go accelerate a lot of the research that they had left behind in their PhDs and postdocs and build practical quantum computers. And so that was my second moonshot, and that's what took me to the field of quantum computing. So I joined Rigetti Computing as an early engineer. I was part of their RF team. And over a couple of years, I went on to lead their hardware team, overseeing all of our cryogenic RF hardware. So my team built and validated many of our company's first cryogenic infrastructure, which became the foundation for Rigetti's early quantum cloud systems. There was obviously a lot of fundamental science and research involved, so we published papers and got some patents for our work. But most importantly, over the course of my time there, we were able to bring actual quantum computers in the hands of users and paying customers, which was I think unthought of, and that was kind of a big leap in the few years that we started this endeavor. It went from being just completely academic to actually something that users were wanting to come test their algorithms on and try running simulations on. So a little bit more about our technology stack when building these quantum computers. So the core platform was based on superconducting transmon qubits, and these operate at about 10 millikelvin. That's pretty close to absolute zero. So we put them in a special cryostat called a dilution refrigerator. It's what you see right here in this picture. So at the device level, we fabricate these aluminum on silicon superconducting transmon qubits, and they have these waveguides and multiple readout lines for readout. And these chips are then integrated into this cryogenic packaging, which has superconducting interconnects. It has an extremely low loss substrate. And then we have an RF, high isolation RF enclosure that usually sits on the top, which prevents crosstalk between the qubits and also prevents the qubits from decohering. And this whole package usually goes right here in the coldest stage of this dilution fridge, where it gets cooled down to 10 millikelvin. And then you have all of the custom cryogenic RF circuitry that is used to control the qubits, read out signals from the qubits. And then finally, at the room temperature side, you have FPGA-based microwave pulse generators and digitizers on the output side, and they're used to control and read out the qubits. So this whole system really works together. It has to be optimized as a single system, all the way from the fabrication of silicon to the packaging to the RF, all the way to the room temperature control system. It all comes together to make a quantum computer. So after Rigetti, I shifted my interest to consumer optics at Apple. I joined Apple to work on next generation optical sensing hardware. So this was a little bit going back into my postdoc research and those roots. The sensors that we developed went into the AirPods, the iPhone, and the more recently released augmented reality device called the Vision Pro. So my work focused on developing and then scaling optical and optoelectronic modules. And these typically included custom photodiodes, VCSEL-based illumination systems, and LEDs, which were typically used for depth and proximity sensing. And I led the cross-functional efforts from the design of these components, the device development, the packaging, testing, for really, really high volume manufacturing. And we took multiple sensor architectures from concepts to early prototypes, put them through some intense reliability testing before integrating them into these products that are going to be used by millions of users. So this was a super exciting couple of years that I got to work on really like the cutting edge of optoelectronic sensors. And then after Apple, I moved on to my third moonshot, and that's kind of what inspired this title. It's called Planet Labs. A move to Planet was more than just a career change. It was really a personal turning point. After years of working on cutting edge devices, something had shifted in me when I became a mom. I started seeing technology from the lens of not just shiny devices and cutting edge specs, but really something that the future generations are going to inherit the consequences of. And so personal electronics, although they were super exciting, I felt like I wanted to focus my attention on something that was truly urgent and planetary scale that was unfolding all around us. I began asking myself, how can I take this passion that I have for deep technology and apply it to something that can actually have a greater impact on humanity? And so over the next few slides, I'm going to share some pictures that were taken by Planet satellites and see what stories they tell us. So this is a picture of the California wildfire season in 2020. More than 4% of the state was on fire that year. This destroyed towns led to extended power cuts around where I live, near San Francisco, and polluted the air to the point where the skies were orange and we couldn't step out without getting headaches. And it's estimated that that year, about 90 million tons of CO2 was released in the atmosphere from California alone. In July of that same year, this is a picture of the last intact ice shelf in the Canadian Arctic. It's called the Milne Ice Shelf. Over a matter of a few days, you can see from our satellite images that that ice shelf collapsed, sending large islands of ice into the Arctic Ocean. It's very clear from these pictures that our environment is in crisis and it's experiencing change at an unprecedented rate. It's already impacting the lives of millions of people around the world. It's costing the economy trillions of dollars. We're also in a very dynamic and evolving geopolitical landscape as countries are facing new challenges from climate change, resource pressures, and populations that are either growing, aging, or becoming restless. Additionally, the global superpower balance around the world has been shifting in the last few decades, with Russia and China becoming more dominant on the world stage. So these are all incredibly complex and truly global planetary scale problems. And we won't be able to solve them until we can see them and truly understand them. And so Planet Labs was founded, and it's run with this exact same mission, where our goal is to image the whole Earth every day and to make change visible, accessible, and actionable. So what we do and what my team does is we design and launch satellites to collect this data. And then there's another team at Planet that builds software to deliver this data to people who need it. And that's typically scientists, governments, businesses, humanitarian organizations, news organizations. And what's really changed in the geospatial and satellite industry in the last 10 years is, we've evolved a little bit from this old idea of what the space industry used to be. There's a new engineering methodology, and it's called Agile Aerospace. It was really pioneered by Planet Labs and a couple of other companies in its cohort, like SpaceX, where we are emphasizing continuous improvement in satellite development. And this has radically lowered the cost of building satellites and the satellite development lifecycle. We've also started leveraging the latest and greatest advances in consumer electronics, semiconductors, automobiles, and leveraging that into space. So things don't have to be necessarily space-rated and go through extremely long, decades-long cycles of proving out space heritage. Secondly, what's changed is data that was once only limited to governments has now been made widely available to anyone on the internet who has a credit card. Thirdly, the rise of large internet cloud platforms and big data tools has made it easier than ever to access and process that geospatial data and to integrate it into people's workflows. So in other words, the barrier to entry to studying the Earth from space has now been lower than it ever has been. So traditionally, Earth observation satellites are rather big. They're extremely expensive, probably billions of dollars, and take a really long time to build and launch. Typically, these missions are like decades long. By contrast, Planet's satellites are much smaller. They're lower cost, and we launch them in much larger quantities so that we can collect much more data at lower cost. And so our basic approach is to break down a single, very expensive mission into many smaller, cheaper satellites in order to operate them as a single coordinated constellation. And there are a few very important advantages of doing this. Firstly, if a rocket fails or a satellite fails, the whole mission isn't lost. You just lose a fraction of the capacity. And so there's resiliency built into the mission architecture. Secondly, it provides you flexibility to upgrade your system as you restock and replenish your satellite fleets every couple of years. So similar to how you might upgrade your devices with the latest and greatest software and hardware, that's exactly what we do with our satellites every year. And in order to do this quickly and efficiently, we are fully vertically integrated. That means we design, build, launch, operate all of the satellite constellations ourselves, including the ground stations. And we also build the software platform that's used to deliver this data to our customers. So this is the constellation that we operate at Planet. It's one of the largest Earth observation fleets in the world. It's designed to operate as an integrated system with each class of satellite serving a very distinct role. So I'll start with the super doves. So these are these are pretty small. They're about this big. They're a CubeSat type of satellite. They are our daily monitoring workhorse. We have about 100 of these in the low Earth orbit, which take images with about a 3-meter resolution. So a lot of the images that you saw earlier in the talk were this from the super doves. And because they are constantly imaging the entire landmass of the Earth almost every day, these are what allow us to monitor and detect change. Next is Pelican. This is our next generation, very high resolution satellite. This is still in development, and the goal is to have about a 30-centimeter resolution with this satellite. Now, we don't have as many of these, and they are what's called a tasking satellite, which means you give the satellite a specific instruction to task it to go see a specific location at a specific time based on what our customers want to. Next is Tanager. This was one of our recent additions to the satellite family that launched just last year. And this is a hyperspectral satellite. So it provides visibility between the 400 to 2500 nanometer range. So really, it allows you to see way beyond the visible. And I'll talk a little bit more about that one. And then SkySats, these are our legacy 50-centimeter tasking satellite. Again, this allows us to do targeted monitoring of specific locations that customers would want. So together, this whole system gives us breadth and coverage all over the globe, and also precision and resolution. So we are able to see the whole planet every day and then zoom into areas that are interesting or maybe want to monitor some change. And the heart of these satellites is obviously the optical payload. This is the payload that takes images from the low Earth orbit, several hundred kilometers away. And this typically includes telescopes, a focal plane array or a detector, and filters or some type of dispersive elements like spectrometers. And all of this is put onto a spacecraft bus and launched. So obviously, you can imagine the challenges of building optics that are able to survive launch and then survive a space mission, which is several years long. So the typical space mission is about 5 years. And so these optics and satellites are intended to survive through the harsh radiation and thermal environments in space. And I think the high G forces that are experienced in launch, those are sort of the two critical parameters that go into designing this system. So I do want to talk a little bit in detail about one specific satellite that we just built and launched, which is the Tanager satellite. This is, like I said, our first hyperspectral satellite. So it was specifically designed to detect methane, which is a super emitter, as many of you may know. It's several times more potent than carbon dioxide as a contributor to greenhouse gases. So the optical design consists of a telescope, which is a 3-mirror anastigmat telescope, and it has a Dyson spectrometer. So because of this design, we can capture a very wide range of frequencies from the visible all the way to about 2500 nanometers with very little aberration and very high efficiencies. So each pixel on this detector is not only a single image, but it actually is a data cube that has a whole spectrum. It has a spectrum with about 400 narrow bands, each about 5 nanometers apart. So this spectral richness is what allows us to see methane, and it could potentially allow us to see all kinds of things across the spectral bands. But right now, the product that we're working on is methane detection, and methane tends to have absorption of light at 1650 nanometers. So that's what gives us the signature when you see when the satellite detects methane in the atmosphere. And the instrument is designed for about a 30-meter resolution on the ground, and it has extremely high radiometric accuracies and signal-to-noise ratios, which allows you to precisely pinpoint and find sources of methane, and also find out the rate of emission and how big of a methane source that is. And then how is it that we're using this? So, Tanager 1 launched about a year ago now and made its first discoveries a few months after launch. So from orbit, the satellite, this was an image taken in the Permian Basin in Texas. So those of you who know, this is a pretty oil and gas rich area. And we picked up a massive methane plume, which was about 700 kilograms per hour. This is, to put it in context, about the emission from like 14,000 cars or something like that. And we shared this data with our partners and the operator of this pipeline. And within few weeks, they were able to find the leak, fix it, and we tasked the Tanager to go back and take a picture of that same area, and we could see that this methane plume was gone. Now, this wasn't just a technical demo, but it was a proof point that this was the first time a satellite detection directly led to a fix on ground. It led to accountability, and this was direct climate action as we could see from space. So I'm going to pivot a little bit and talk about, when you're working on moonshots, one thing is for sure, like failure is not an option. It is inevitable. In moonshots, the cost of avoiding failure means that you're not learning fast enough, or you're going too slow, or you're not really doing anything. The goal should not be to eliminate failure. It's to make failure small and safe and informative so that you can move forward. So this is something that's used in industry pretty often. It's called failing fast and failing forward. And that rings very true, and I hope all of you remember that when you're working on your research or your projects or other things. In every project that I worked on, I think I've definitely failed more than I've succeeded. And going back to my graduate school days, it could be a device that didn't laze. It could be qubits that didn't have the right coherence. It could be a satellite that you've launched and is not in focus. I think along the years, I've stopped treating failure as a verdict or like an identity. It's really just data. It's giving you feedback about the system, and it allows you to adjust your mental model or your model of the system to now be more accurate to the physics or reality. These are also the moments where you really build humility, perseverance, and resilience. And it's also, you learn the best lessons through failures. And you have the best stories to tell through failures, which is why I'm talking about it. So I want to start with one of my early memorable failures that happened right here in Michigan during my PhD. It was like a few doors down from where we are right now. We were doing a growth run on an MBE system when a small coolant line on this RF nitrogen plasma source burst. In a matter of minutes, this gallons of water dumped straight right into this ultra-high vacuum chamber, which was doing a growth at 900 degrees Celsius. It was exactly as bad as it sounds. We had to completely open up the system, clear all the water, bake it out for weeks, replace all of the O-rings, regenerate the cryopumps, recalibrate, every single effusion cell and verify vacuum integrity and so on and so forth before we could bring it all back online. It delayed our experiments for months, and at the time it felt catastrophic. We didn't know what we were doing. There was no textbook or handbook or no chat GPT to tell us what to do at that time. We would just brainstorm ideas with Professor Bhattacharya. We would contact the manufacturer, who was not very helpful at the time. But really, we just took it one step at a time, day after day. It was one of the most, looking back, it was one of the most valuable experiences in my early career, because it forced me to learn to recover from failure and work methodically under pressure through like a systematic design of experiments and debug a complex system through a logical series of experiments. And doing all of that while staying calm and staying positive. And that mindset has stayed with me, and I've used it many, many times in all kinds of problems, just in larger scales. In fact, I learned so much about vacuum systems through this experience that I could directly apply it to when I was working on the MOCVDs or the dilution refrigerators in quantum computing, and even now on satellite propulsion systems. There's like parallels in how all of those work. Another one of my favorite failure stories comes from my time when I was working at Rigetti Computing, and we were developing our own Josephson parametric amplifiers. So these are superconducting microwave amplifiers that give us extremely low noise performance on the qubit readout. And during the testing, we started noticing really strange behavior. The gain would drift, the calibration floor was really unstable, the calibration wouldn't hold, the noise floor was all over the place. And for weeks, we chased down everything. And like I was looking at all of the usual suspects. Is it the fabrication? Is it the cabling? Are there the flux lines? But nothing explained it. And finally, we realized the culprit was not inside the cryostat at all. I was sitting on it the whole time. It was a chair. It was a steel chair that was in the lab. The ferromagnetic metal was distorting the flux environment in what, these are called squid loops. They are two Josephson junctions, and they're extremely sensitive to magnetic fields. So the fix was pretty straightforward once we could see the correlation. No steel in the lab, obviously, and also better shielding for these highly sensitive devices. So this was another unforgettable lesson, that when you're working at the scales where you're doing these measurements that are extremely precise, everything becomes part of your system design. Like it's not just about the system, it's also about the environment. So I wanted to walk you guys through a few lessons and takeaways that I've learned along the way. The first one is focus on first principles. I've moved between a couple of different domains, from like optics to quantum computing, consumer space, and satellites. On the surface, they sound like they're very different, but actually they're not as different as you might think they are. The terminology, the acronyms, the software that engineers use in these fields, the materials, obviously those are different, but the principles and fundamentals remain the same. Your signal integrity, noise budgeting, interfaces, how you calibrate systems, how you have margins in your system, how you document your system design. Those are all universal and applicable everywhere. What carried me across each of these moonshots wasn't just sort of memorizing some right tool or knowing some piece of software, but it was really being fluent in the concept enough to go into a different field, to understand those constraints, and then like apply those same fundamental principles there. So Tools will keep evolving, and you should definitely learn how to use the tools that you're learning in class today. But remember that the fundamentals are what are going to be applicable like 10 years from now. The next piece of advice I would say is build something end-to-end. This could be a project, it could be part of your graduate school work, it could be something outside of school, or like solar cars. It could be many nature of things, but I think building something end-to-end really is an experience that's super valuable when you go out in the industry. I think when you build something from an initial concept and you're responsible for something from a concept to design to debugging it, gathering data, analyzing what's going well and what's not going well, what I call the full stack experience, it's really giving you a view into system thinking that is very critical in the real world. In my PhD and every experience after, because of being able to work on things end-to-end, I was able to constantly move up and down through the layers, from small design choices to system-level outcomes. It forced me to not just see the system as a bunch of individual components, but I could see how everything was interconnected with each other. And this naturally evolved into system thinking. And this mindset has been really valuable in what I do now, where I get to lead large programs and systems across like really cross-functional teams. So that is another strong recommendation, to go build something end-to-end. The next one is strive for iteration over perfection. So when it comes to building complex systems, you can't always plan your way to perfect. You have to prototype your way there. There's a common saying, again, that I've heard in the industry a lot, is perfect is the enemy of the good. So if something is good enough, build it, and then there's going to be no sort of mythical right design waiting for you. You really have to build something, break it, and learn why it doesn't work so that you can improve quickly. So, when it comes to working on these complex projects, maybe some of you, you've heard about this. This is pretty common when you're working on moonshots like quantum or space, where there's the traditional approach, which is not very agile, or the traditional waterfall approach. You typically have very low risk tolerances. Your mission has very high requirements. Failure is absolutely not an option. Risks must be carefully anticipated, planned, mitigated before you, even start doing anything. As a result, you have a really large number of requirements, and your project can get pretty bloated with cost and requirements and timelines very quickly. And as opposed to that, I think what I've found, especially when working in these moonshot type of projects, is the contrast is agile engineering. It relies heavily on iterating between functional prototypes and progressively making your device or your product more feature complete and more performant over time. So sort of a simple cartoon to explain this concept is, suppose you're trying to go from point A to point B. You've decided that the car is the right way to do this. So in the more traditional approach, you would build a wheel, build two wheels, design an axle, body, chassis, and then eventually 4 steps later you have a car. But the agile approach would be asking yourself, what's the cheapest, fastest way of getting from point A to point B, and doing that first. And then progressively improving it, making it more feature complete, making it safer. But as a result of this, you've gone from point A to point B a lot faster than you would have. You've got feedback on the road. You've got feedback on all kinds of things as you've made the journey 5 times now. And lastly, I think I want to close with I think the most important lesson that I've learned, which is communicate and collaborate as hard as you engineer. This is probably the biggest shifts that I've experienced as I moved into harder and larger scale systems, and realized that just being technically brilliant isn't enough. It's often hard for us scientists and engineers to internalize this, as we tend to have a culture around lone wolves and just kind of doing your own thing. But early on, when you're working on something simple and it breaks, you can go fix it. But when you're working on challenging problems, no one person is going to have all the answers. You really need to rally together with a team that each brings its own skill sets and expertise to the table. So when working on quantum computing, when we saw a qubit that needed to be debugged, that meant pulling together fab engineers, packaging engineers, RF engineers, control systems engineers, physicists, and collectively kind of translating what we knew about the system into kind of one source of truth. Similarly at Apple, when a device would drift out of spec, that meant we had to get engineering and all the way to supply chain, production, everyone working in lockstep and working as a single brain. I think your ideas are only effective if you're able to communicate them and you're able to get other people to rally behind them and you're able to stay aligned on them. So I think that's probably one of the most important lessons is learn how to collaborate and communicate in a team, because that's probably what the real world is going to look like. All right, so that is all of the content from my talk today. I would love to stick around and answer any questions that you might have.